Hello everyone, my name is Heng, and today we're going to talk about the fractal generated by modifying aperiodic substitution tiling. So the aperiodic substitution tiling, today we are using the armchair tiling. And fractal, by definition, fractal is a complex geometric shapes with fine structure at small scale. So here is an example, a Cantor set. A Cantor set is just taking a meter 1/3 away every generations, and it forms a very fine structure thing, a fractal. And this fractal often come with a certain amount of self-similarity. For example, here you can see these shapes and these shapes is the same. Yeah, it's just in different place. So here is the similarity dimensions, and the definition is n equal to r, the equations. And here is the number of copies, and the r is the scaling factors, d is the dimensions. So here is an example. We know that straight lines, of course, dimension is equal to 1. If we scale it by 2, means r equal to 2, it becomes 2 copies of itself. And for d equal to 2, a square, for example, when we scale it by 2, it becomes 4 copies of itself. So here is like fulfilling the equations. And when d equal to 3 is same, we have 8 copies of itself, and we scale it by 2. So like the cubes, 8 copies. So just now we have defined we have checked on the integer dimensions like dimension 1, dimension 2, and 3, and that is something dimension that is not integer. And here is an example, a Sierpinski triangle. A Sierpinski triangle is a triangle that you always take the middle triangle away. So you can see these shapes after you take away again and again, and this having non-integer dimensions. So how do we calculate? We can look at the triangle at the bottom left. Then we'll try to scale it by 2. If we scale it by 2, it becomes the big triangle. It has 3 copies of itself. Because the middle triangle doesn't count, it's just empty, right? So it becomes 3 copies of itself. So n is equal to 3. And we know that we scale it by 2 is r equal to 2. Then we can slowly come up with this answer. The dimensions approximate to 1.585. And this makes sense because we take away something from a square, and for a triangle, we know that a triangle plane is d equal to 2. So we take away something from it, we should expect dimension is lower a little bit. So it's come to 1.5 something. It still makes sense, I guess. So later we're gonna use this armchair tiling to generate a fractal. So here is the armchair tiling, and armchair tiling consists of 2 colors. You can see here is the yellow color. We call it a small tile, and this is a big tile. Because the small tile is smaller than a big tile, so it's called a small tile and a big tile. Yeah, so on. We can generate this armchair tiling using substitutions. Here is the substitutions. So we know that this is a small tile and this is a big tile. And here is the algorithm. So the algorithm saying whenever there is a small tile, we replace it with a big tile. And whenever there is a big tile, we replace it like this, a big tile and a small tile. So in every generation, for example, here is generation n, we find that is some certain tiles like this. Then when we go to generation n plus 1, we just replace it with this order. And something to remark that is the big tile is larger than the small tile, means the 5 to the power of 1/2, and the 5 here is a golden ratio. And another thing is the boundary shapes, the boundary signs remain unchanged, considering this boundary, the boundary of big tile. When we replace it with a small tile and the big tile, the boundary that remain unchanged, but just the tile getting smaller. So the big tile on the generation n plus 1 is much smaller than the tile in generation n. Then how much smaller is also by a golden ratio to the power of 1/2. Here is an example of how we grow in armchair tiling by substitutions. So you can see that the tile is getting smaller, but the region is remain the same. So yeah, here's the pictures, and we name it as the generation by its number, means we start with generation 0, 1, 2, 3, and 4 like that, and so on. So maybe you can go to Gen 5 and so on, Gen N. So we generally call it Gen N, yeah. And here is the N substitutions. So N substitution is a higher order substitution that we make the move faster. So we jump 5 by 5. So just now we used, like here is Gen 1, means it's a big tile. We just now use it at a big tile and a small tile to a big tile, right? So here is Gen 0. And Gen 1 to Gen 2 just now. This is the typical substitutions, but now we using it, change it to Gen 5, so means it's much faster. But somehow we should expect it, the final thing means when we go to infinity, the structure is going to be the same because we just speeding it up, but we didn't change anything. And here is the result. It's jumping much faster. You can see the tiles are getting smaller in a faster speed. If it's in this case, the 5 is smaller by a speed of maybe 5/2 because we know that it's 1/2 just now and it's 5 times faster, so it's something like that. So, and when we're doing a N substitution, we just take the 5 away, we just sub the N instead. Yeah, it's something like this. And meanwhile, when we try to generate it, right, we still are facing a problem, is that we're still dealing with tiling. We just plane with different shapes in it, with very cool shapes in it, but it's still a dimension 2 stuff. When we're doing a fractal, we often want to maybe having a dimensions not 2 or not 1, we just something have a decimal in it. So how we do it is like we refer back to how a Sierpinski triangle does. Sierpinski triangle doing something like we take away the middle triangle again and again, right? We remove certain parts of it. So same goes to here. I mean, having a N substitution, right? For example, here is a 5 substitutions. A larger substitutions allow us to have more room to make modifications over here. For example, I remove one parts from here. I assume it's a big tile, if I'm not mistaken. So I remove the exact same region over here. Here's not a big tile, a small tile and a big tile. Because it's after a generation, right? Here is Gen 6. So the tile is getting replaced already. So we remove the same region, just as long as it's the same region. So it will stay consistent after all. So this substitution, we call it as a 501 substitutions, and with certain tiles removed. So 5 here is the N substitutions, and 0 is the number of small tiles removed, and 1 is the number of big tiles removed. So here's a big tiles. Let me do some edits. Here is a small tile. So in this substitution, we call it as a 501 substitutions. So we just remove certain parts and we see how it goes in substitutions. So here is an example. You can see that the small parts over here, right? Here is the part we remove, right? It still remain there. And you can see certain parts is getting removed over here and here, over here, and so on. So here is the effect of after I'm removing this. And with this, we can calculate the dimensions. So you can see from the pictures just now, we have a small tile over here, if not mistaken. With a small tile, something like this, look like this before. And here is a big tile like this. Yeah. So this small tile, right, if you try to zoom it out, it's actually, if you try to maybe make it like this, make it a larger bit, then here is a larger, scale it. Then we do a rotations. We can see actually the shapes, right, is gonna be identical. So there's something interesting about the fractal. So because this fractal having a cell similarity, a very high cell similarity. So after I zooming this out, every single tile I can say. So maybe this area also works. After I zoom out, then make it the same size as this one, then we can check that it's actually the same shapes. Then we can use this as a fact to calculate the dimension. So before we calculate the dimensions, we have to count the tiles first. So because we know that we use is n equal to rd, n equal to RD in the definitions, right? So the dimension definition. So before everything, we have to figure out how many n's are there, how many tiles are there. I will skip it to the n, to the results. So here is Sn is equal to Fn. So Sn over here is the number of small tile in generation n. So number of small tiles in it, and here is the number of big tiles in it. In Fn is Fn, and here is Fn minus 1, and small tile is lesser. Okay. So after we have this, then we can go into calculate the dimensions, evaluate dimensions of 501. So in this 501, okay, we're using the same definitions, the dimension definitions. When we scale it, it is by 5 n over 2, and in this case n is equal to 5, so it's 5 over 2. Another thing to mention is that we know, let me change color. We know that this part, after we scale it by 5 n over 2, it's gonna be this big. And at the same time, how many copies of itself? We can aware that we have 1 copy of itself, 2 copies, and 3 copies. Means that 3 original copies of itself, because this is generated by a small tile. Remember, if in Gen 5, right, if we consider a Gen 5 tile, this is exactly 1 small tile positions, the region of 1 small tile covered. And this another 2 parts over here is another two small tiles. So we know that that is 3 small tiles parts, and there is another 4, 1, 2, 3, 4, another 4 big tiles. But because it's bigger, right? So the factor must be a bit larger, and it is scaled by 5.5 to the power of d. And I can explain later, but it's scaling by certain amount because it's larger, a little bit larger, so it plays a bigger role. And we can solve this equation. You can solve it over here. We just solve the equations, then we replace using some sort of technique. Then we can get a d is equal to 1.848. So we are ready to generalize these theorems to NAB Armand-Chair fractal. So this theorem is to calculate the dimension. After generalize, we know that the d is equal to 2 log 5x, and the x over here is the solutions of this polynomial. So this solution equal to 0. Then we find there is only exists 1 positive real root. So there's no confusions like which x to choose. So in this proof, right, is actually doing exactly the same thing as we had before, the 501 Armand-Chair fractal when we calculate the dimensions. Doing the same thing, here is RD equals to n. And I think something worth mention is that the scaling factors over here, I will explain it. And we know that here, this part we already mentions that is 5 n over 2 is because of the scaling, and to the power of d is equal to the number of small tiles. But when we go into big tile, right, because the size is bigger, even though the inside is the same, but it's bigger, so we have to scale by something. But what is this factor? This factor is because the 5/2, I think we have introduced it. The 5/2 is because we know that a small tile is smaller and the big tile is bigger. And how much is bigger? Is bigger by 5 to the 1/2. If, for example, we're having a small tile, we have to scale it by a certain amount in order to become a big tile, and this amount is the 5 to the 1/2. But in this scaling, right, we cannot just and over here, right, we cannot just multiply by half, but we have another d over here, the dimensions. Why is it this case? It's because we are considering the something like region. So after we scale, right, for example, if it's area, we have to the power of 2. So here we are talking about the region, so it's not just 5 to the power 1/2, it's 5 to the power 1/2 to the power of d over here, because it's not just region, but the region of a fractal. A fractal is having a dimension d, so you have the power of dimension d. Other than that, I think we're doing roughly the same thing. We just take out substitutions and we form this polynomial. Substitution x equal to 5 to the power of d over 2. Then we got this. If we solve this equation, we're having the x value, and we just re-express the d in terms of x, then we can just having the equation in the theorem like we had just now. So here is a distribution of the dimensions for the case n equal to 10. Using the theorem that we had just now, we just calculate every single possible fractals of n equal to 10. So it's like 10ab. In this case, 10ab, right? At the start here 0, we just didn't take away any tiles, so it's 10 0 0 and 10 1 0 like that. Take 1 tiles away, 1 tiles away, again. So we just able to draw this graph. So in this graph, right, something interesting is that the 2 over here and the 0 over here. So it's upper bounded by 2, I think is already quite common because we are taking away something from a plane. So it's decreasing from 2, I think it's expected. But something interesting is after 1. So this part. We know that we often expect something dimension lesser than 1 is a straight line. It's like Cantor said, we try to take away something from a dimension 1 stuff. For example, we erase from one line to one for 2 parts like that, removing away the middle. So this is lesser than 1. Having a dimension lesser than 1, this is something we can expect. But now we are removing from a plane like that, we remove some certain parts of it, and it's making it lesser than dimension 1 is something interesting for personally. I think it's quite interesting. Another interesting thing is that from this graph, we can see that it's straightly decreasing, and it's decreasing in a faster rate, means at the end is faster, it's sharper. This means like if I take away 1 tile at the start and I take away 1 tile at the end, means the change, right? The change onto the dimensions is more effective over here instead of here. So when there's less tile, the change in number of tiles is make even bigger impact onto the dimensions. Yep. So after we have observed the graph, we see something like this. To me, it's a bit feel like it's an interval because it's between 0 and 2. And if it's interval, it's going to be very convenient because if it's like interval 0 and 2, we can just pick whatever x in it. Then we can find interval. We can find a fractal with respect to these dimensions. For example, we take x equal to 0.1 maybe. Then we can straight away find, okay, we can confirm that always exists such a fractal that having a dimension equal to 1. That's very convenient, right? But it's not the case at the end. We are hoping to have an interval, but it's not. So this is by some knowledge in general topology. So we know that interval is uncountable. And we know the set of the dimensions, right? We are formed by NAB. So we're doing all the NAB, all the stuff, NAB, Armand-Chair fractal, substitution and stuff. So all the dimensions are coming from this NAB. So here is the arguments. So NAB are countable sets because they are natural numbers. So two of them together, unions together, or product together, also a countable set. So after all, it's still countable. And an interval is not countable, so A is not interval. But we can go for some weaker statements. Something is countable, maybe countable, but meanwhile is very useful. Here is so you introduce something like a dense. We expecting this is a dense set. So here's the idea of the proof. It's already proven. So dense is a weaker statement, but then saying if we have any x in 0 and 2, it's not as good as we can just having any x, then we can always have a fractal. But if we have a x, we can always search that always exists a d that is ultimately very, very arbitrary close to x. And this d are having a fractal. So maybe x is maybe a 0.1, and we always exist a d such that maybe d is 0.100001. It's very, very close to x, and we can find a fractal for this d. So here is an idea of proof. This is the algorithm for 501. as we know before, the 501 substitutions. So in the 501 substitutions, we are taking away this region. If we consider a region-wise, right? If we consider a region-wise, right, we are taking away these regions. But what if we're increasing the number of n? For example, here, we increase the number of n. We're taking away the same regions. The 501 substitution, we're taking away the same regions, but we consider a 935 substitutions, and we are taking away the exact same regions. Inside here, there is 3 small tile and 5 big tiles. So we're taking away the same exact regions, just the number of tiles is different, but it's actually the same thing. So we should expect that even though the tiles look like smaller and so on, but the region taken away is the same. So the dimensions are the same. So D is equal to D prime. The dimension over in 501 and the dimension in 935, it should be the same, because the region taken away is the same. So if we consider this same thing, the same region taken away, but we take another extra region, a small region, we can say it is not the same. The dimensions is not the same. We're doing the substitutions, 936 substitution instead of 5, we do 6, another extra tile away. We cannot say is D prime D equal to D prime. Cannot say D is equal to D prime. It's not equal, but it's somehow similar. It's very close. It's approximate, right? Because the very little regions is make very less impact onto the dimensions. But what if we take this n, because this is still quite similar, right? It's still quite big, relatively bigger. But what if we take this 9, instead of taking 9, we take n goes to infinity. So we're having exact same regions, then we take this away these parts, take away exact these parts, and we take another even smaller one. Instead of this one, even smaller. For example, just this part. Yeah. So as we take n goes to infinity, it is possible for how small we want to, like just as small as we want. And this make, if we take the limits of n goes to infinity, there always exists such a fractal with dimension d prime is equal to d. As you take the limit of d prime like this, and we take the n goes to infinity, the d prime is going to be almost exactly the same as d. This proves the collections of all the dimensions are dense. Because of these statements, for every d, we're able to find such a d primes, a sequence having the, just take away another small tiles, and it's gonna be the very close to each other, and this make a dense set. And here is our proof. So here is an example of some fractals. You can see how it generates. Here is a 310, 7, 5, 10. So you can see the dimension is very close to each other. So I personally picked that it is like a dense set like that. You can see it's very close to each other. While another version is this one. This is more interesting because it is dimension lesser than 1. But it's more interesting in terms of mathematical, but it's not the picture. The picture is it's more boring because it's just very less stuff. So that's all for me. And here's my email and the code I generate the fractals. So you can check over here. In this code, you can change your n, a, and b to generate a fractals, and change the value of k, how many generation you want to generate using these NAB substitutions and stuff. And here's my email. You can contact me if I have any questions on the coding, or maybe on how to use this code, or maybe how the content today. And we can solve the question together if there's any big question over there. Yeah, that's all for me. Thank you very much.